Okay, everybody, welcome back to our second and final lecture of Module 5. Here we're going to talk about uh, the P.05 criterion and effect sizes. So let's go ahead and jump right in. So where did P.05 come from? Pay no attention to the unicorn here. I was supposed to animate it in, but it's already in. So in science, our criterion or our alpha for the null hypothesis significance testing is that our data need to be rare enough for us to reject the null hypothesis. It tells us to reject the null hypothesis when the probability of our results is less than 0.05. But where does this come from? We tend to think of statistical analyses being conducted in an alternate universe in which we assume that the null hypothesis is true. What is the null hypothesis? Well, say you have an intervention in which you look at the effect of a drug on a particular psychological disorder, and you want to see if it reduces it. You can actually compare the group of people who take the drug to the population and say, is this different from the population? How different? It comes up with a p-value. How far away is this from the mean? Okay, this is all based on sampling distributions, and we tend to look at and think of our sampling distributions as another universe, where we always assume that every sample that we draw from the population should be equal to the population. You could think of this universe as a one where unicorns have bad body odor. You could think of it as one where all rainbows end at an Arby's. No, I'm just kidding. But really, in this universe, it's an imaginary world where we always assume that the null hypothesis is true. So your p-values are the probability of the result that you got in this universe. In this universe, it represents the probability of our data in this world. And when we find that that data is sufficiently rare, we say, let's reject the null. But what is our criterion for rarity? Our criterion for rarity is the idea that it's less than 0.05, but where does 0.05 come from? Well, you're not going to like what you're about to hear. It's completely arbitrary. It's completely arbitrary where that comes from. Okay, so here, we'll go back to that. Again, this represents the probability of your result if the null hypothesis is true in reality. That's what P represents. P is, so let's look at the red distribution here. That's the population. That's the population. And and the blue is your actual data. So the p-values tell you how far your data falls from what you should have expected. This is why we use control groups that represent the population in our science. We compare our experimental groups to those controls and how far away the means fall from each other. We can say that it's different from the population or different from what we should have expected. And so that's what we're doing here. But there's some big problems with these p-values. Let's go over these problems. You can get a significant result by adding more participants to your study. Just by increasing your sample size, you can get p to drop down below 0.05. You can get significant results by chance. We are in a world where we're basing things off of probability. What's to say that you didn't just get lucky and draw a sample that was different from the population? We call this a type 1 error. And a type 1 error is when really, in reality, the null hypothesis is true. The drug doesn't work. It doesn't reduce anxiety symptoms, for example. But your statistical test leads you to think that it does. That's a type 1 error. So you can get a statistically significant result by chance. And you don't know, there's nothing about your statistics that tells you that result is wrong. You can also get non-significant results by chance. This is called a type 2 error. So this means in reality that the null hypothesis is false, but your test leads you to reject the null. Or in other words, the drug really does reduce anxiety symptoms, but your statistical test leads you to say that it doesn't. Okay, so here's some problems with statistical testing. The p-values, that statistic is based off of a bunch of different variables that go into a statistical model. Okay, so that's a big issue. Another issue is that null effects don't necessarily mean that there's no differences between your groups. This is similar to the type 2 error, but say for example, you have a study, this is the same figure as before, where there's a difference between your means here. There's a difference between the red group and the blue group. But let's say that that is at a p.07. We would say that there's no difference here. Clearly, there's a difference. So just because you have a null effect doesn't necessarily mean you have a nil effect. Just because you have a null effect doesn't necessarily mean you have no effect at all. It just means that in the universe in which we test our hypotheses, your data were not sufficiently rare enough to say that the result was significant for you to reject the null hypothesis. So what do we do with all these problems about p-values in our mind? So here we can remember that statistics can be generalized. So when you get a result in a regression, you can generalize your B estimates to the population. You can generalize your confidence intervals to the population. When you get an F result in ANOVA, you can generalize that to the population. Every statistic that we get can generalize to the population. So when we're generalizing using our p-values to help us generalize, we want to make sure that they're relatively stable. Well, guess what? None of these are actually stable. They're all tenuous. They're all influenced by different variables like your sample size, which I alluded to before. So one way to get around this, one statistic that we're really interested in generalizing are what we call effect sizes. And you already know a whole bunch of effect sizes. Effect sizes refer to a way of quantifying the difference between two or more groups, or we could quantify the strength of a relation in regression or chi-squared, so that the units are more psychologically meaningful and they're independent of sample size. So the sample size won't influence them. We take into account the sample size. So you know a bunch of these already. You've looked at Kramer's V. You've looked at eta squared in ANOVA. You've looked at Cohen's, no, excuse me, not Cohen's D yet. You looked at big R squared in regression. You looked at all of these. And I'm going to talk about a new one today that you've not encountered yet. It's called Cohen's D, where you're going to be comparing two groups to each other. So when we use Cohen's D, we put the standard deviation of the two samples in the numerator, so standard deviation, and the difference between your means. What this equation does, is it allows us to look at the mean difference between two groups and then put it into standard deviation units. So it allows you to quantify this in a way that folks who are not familiar with the scaling of your measures can look at it and say, oh, this group is this many standard deviations away from the other group. And the cool thing about standard deviations is that they're not influenced by sample size. Okay, they're not influenced by sample size. They're said to be relatively stable among any sample size. So here you take the difference from one group to another group, and then you take out the pooled standard deviation between the two of them. So again, this tells you how far apart your units are in standard deviation units. So you could use this in a t-test. You could use this in an ANOVA if you want to compare two groups, even if you have three groups. There might be two groups that you're really interested in comparing. Or you could do this for all of your groups, all of your comparisons in ANOVA. Okay. And again, we use this in ANOVA for eta squared, something similar that we get. Cohen's d is a little bit stronger of a measure than eta squared because it, again, literally allows us to quantify how far apart means are in standard deviation units. Eta squared doesn't do that. It tells us the amount of variance accounted for in the dependent variable by the independent variable. Kramer's v and r squared also tell us that. So let's get some practice with a calculator, calculating some Cohen's d's. So let's first look at this example here. So let's say that 10 individuals in a Stroop interference condition took longer to finish a color naming task than 10 individuals in a no interference task. And you've got your means and your standard deviations. And your sample sizes of each group. So there's 10 people in each group. And those are the three things that you need to calculate a Cohen's d. You don't need t. Okay, so we can see that this relationship is significant. But just because it's significant doesn't necessarily mean that it's practical. So we can make it practical by saying, how many standard deviations apart is it? Okay, so I'm going to stop sharing for a second here. And I'm going to show you where you can find this calculator. So you can find it here under Module 4, down at the bottom, effect size calculator. I'm going to go right to our calculator and allow you to take a peek. So here, I'm going to add in some of the results. Okay. So hopefully everybody can see. I'm going to just double check the Excel file. And I'm going to add in our results here from the PowerPoint. So one group had a mean of 42 seconds, and the other group had a mean of 22 seconds. Both groups had standard deviations of 10, and both groups had sample sizes of 10. Okay, so what this calculator does, you can see, calculates Cohen's d. So if I were to ask you how many standard deviations apart are these two means, you could say 2. And that's a huge effect in psychology. It's a huge effect in psychology. Okay, so I'm going to delete these here. And we're going to go do another example. So let's go back to our PowerPoint. And we can say that these are 2 standard deviations apart. Again, you find that effect size calculator on Cougar courses. But let's go ahead and do another example. Now, in your training, you've been trained to look at t-values and p-values to tell you how far apart differences are. And on the surface, this study here with 10,000 Amazon workers receiving sensitivity training showed less racial bias on the IIT than people receiving no sensitivity training. This looks stronger because you've got a t-value looking at how far apart their means are. But remember, t-values and p-values are influenced by sample size. We've got 10,000 Amazon workers here. Let's look at this study here where there's behavioral mimicry, where we synchronize by tapping one's finger with a different race stranger. So you tap in synchrony with this person, and there's some research that suggests like marching in unison with each other can be really good for building bonds between people and making groups more cohesive. Maybe that might be better than racial sensitivity training, but on the surface right now, look at this. So we've got some scores where we're comparing the means between folks on the implicit association test, but look at the t-value, it's smaller. So if you were looking at these 2 studies, you might assume on the surface, hey, let's give people racial sensitivity training instead of doing this behavioral mimicry task. But that might not be the way to go because we know that t-values are sensitive to things like sample size, and that really can hide the strength of an effect. So let's go back to our data here, our Excel calculator, and take a peek at the comparison between these two groups. So you can have your PowerPoint pulled up, but let's say that the racial sensitivity training group had a mean of 0.45 and the control group had a mean of 0.55, okay? And we have two standard deviations, one of 0.2 and 0.17, and we have 5,000 people per group, I think. Did I get that right? Yeah, so we've got a Cohen's d of 0.54, negative 0.54. So what that means is that this racial sensitivity training reduced the bias on the implicit association test by 0.541 standard deviation units. I'm going to mark that over here so we can remember. Okay, so 0.541, this is sensitivity training. Okay. Now let's look at the behavioral mimicry task. Okay, the behavioral mimicry task had a mean of 0.22 and the control had a mean of 0.55. And they had standard deviations of 0.20 and 0.23, okay? And they had sample sizes of 20. Okay. So mimicry is at negative 1.535. Okay, and this one's at negative 0.54. So look at the huge difference there in effect sizes. Now, if we were to look back at our PowerPoint slide where we see the t-values, we would probably think that the sensitivity training is working a lot better than the mimicry training. But when we look at the effect sizes that are not based on sample size, we find that that's not the case. It's actually the mimicry training that's better. And we can objectively say that the mimicry training is better because of the effect sizes. So this has got an effect size of negative 0.15. It reduces the bias by 1.5 standard deviations. That's huge. Whereas this training, which we actually know from research actually doesn't work very well, the sensitivity training that corporations do, it doesn't really work. Let's say it reduced the strength of the effect by 0.5 standard deviations. So what I just showed you here in this lecture is the second lecture is probably going to come up on a question in exam 1. You're most likely going to get a question on that about effect sizes that ask you to compare its usefulness to other statistics. And I may even ask you to look at 2 samples and say which one's stronger. Okay, so hopefully you were paying really good attention here, because you're probably going to get a question similar to this one on your first exam. Okay, everybody, well, that does it for this week. I will go ahead and catch up on our next lab class, where we talk about our major projects for the rest of the semester. Take care, everybody.